Friends, starting with today, 14th episode of Nodutalk, we are going to cover problems in ductile iron, which is quality-related problems in ductile iron. In past two issues, we have covered other two topics of the problems in ductile iron. Today's topic is going to be covered by Mr. Staff Hendrieckx. Past two episodes, we have covered material-related problems as well as dimension-related problems in ductile iron. Now, in 14th episode, we are going to cover quality-related problems in the ductile iron. Today, this is the content of the today's topic, problems in ductile iron quality-related. Then we are going to cover a porosity, air or gas inclusions, general inclusions, cracks, then destructive testing, NDT testing. Over to you, Mr. Hendrieckx.
Good evening, everyone. Today we will have it about the integrity of the casting section, not about the surface, but mainly the section. The requirements about the casting sections are given by the customer and depend on the application of the casting. The requirements come on top of the material requirements, and the quality has an effect on the strength and fatigue resistance of the casting. Because the material requirements, that's just the material, but the quality of the section can influence it very, very much. And only the customer will decide about the allowed presence and tolerance of quality-related items. The foundry has to accept these requirements as well as the testing methods. I always should advise you to assure that the testing method is available and agreed upon. A requirement as is free of any defect as our porosity, inclusions and cracks is never acceptable for the foundry because nearly no casting will meet this requirement. It is the same all over the world. A customer who doesn't know anything, he just likes to put this sentence on his order sheet and his requirements. Please discuss in front of starting with the customer about. What features do we have mainly? That's porosity, air and gas inclusions, other inclusions and cracks. These are the four major items involved, and the testing is destructive, non-destructive, and a casting test in working conditions. At the end, we will add the nodularity and your nodule count because some of the customers can ask it, although it's not in no international standard available. So porosity, that's an area without material due to the non-compensated volume shrinkage during the liquid cooling and solidification. Every material shrinks during cooling and mainly also during the solidification. And if that's not compensated, it will give a porosity. We have micro porosity with rough surfaces. We have micro porosity with smooth surfaces. We come on the difference later. We have micro porosity. And we have sunk in, and sunk in is something that's mostly not recognized by most of the customers and foundries as a shrinkage, as a porosity, but it is. Excellent. Here we can see some examples of it, and that's on pump casing, and we can see a micro porosity and a detail from it. It's small, but it's micro porosity, and under it there's a rough wall surface, but that's not the porosity, of course. And we can have open cavity when the porosity is coming to the surface. We have sponge-like porosity, we have rough irregular wall surface, and we have surface depression as already said. A porosity will reduce the strength and effective life, but mainly also leak tightness if it's used in castings like a pump casing or a valve or whatever. Here you see some real porosity, micro porosity with rough wall surface. This is mostly happening when the carbon equivalent is lower than 4.3, but can also happen in somewhat higher. But rough surface is mainly when the carbon equivalent is less than 4.3. Here you can see that many times located in a hot spot, because the hot spot is the last solidifying area, and if there is no compensation, then we have, of course, that porosity. It's for that reason due to insufficient riser activity. If the riser does not deliver feeding metal until the last second, it will lead to a porosity. And it's mostly with a lower CE, lower than 4.3. If we make an inventory of possibilities, it's improper feeding and rising, of course. That's the main root cause of a microporosity defect. It's in a hot spot. When we have a hot spot, many times the hot spot is not connected with the riser. If it's not connected with the riser, it can have these type of defect. Low nodule count will also increase this shrinkage tendency, while a low nodule count indicates a low feeding capability, and then it will increase the tendency to do it. High shrinkage tendency, we have high carbon equivalent and alloy levels increase the shrinkage, but this is not with a rough surface, but it will then get a smooth surface, but I come on that later. Improper inoculation, of course, if you have an improper inoculation, you will have a low nodule count, and a low nodule count increases the tendency. Improper pouring temperature, that's another thing, because if the pouring temperature is high, we first have liquid metal shrinkage between the pouring temperature and the start of solidification. This shrinkage is already to be compensated by the riser, and then later he must also compensate then the solidification shrinkage itself. It's better to have a low pouring temperature. The mold hardness variation, we have seen it in previous sessions already. There is an expansion in ductile iron during the solidification. When the mold is not strong enough, not hard enough, that expansion will push out the mold, and that extra volume that it makes can lead to porosity, microporosity appearance. Then the section thickness variation, of course, it's when we go from a thick section to a thin section and again to a thick section, that will block the feeding capacity of risers, and if the feeding capacity of risers is blocked, we can have this microporosity without any problem. We have other possibilities. Sand erosion. Weak sand is eroded by molten metal flow. Let's say that's a rough surface, but it's not a porosity as such, and it will not happen in the center of a section. A poor mold finish, that's again the surface, but it's not okay, and that will be taken in next session. Coarse sand grains gives a rough surface, of course. Low mold strength gives a rough surface. Metal penetration we can have if the mold is not ramped properly, then the metal can easily penetrate, and if there is no good coating on it, it will penetrate. The excess of pouring temperature will also give a rough surface, and a high turbulence of pouring will also give a rough surface. So this is a rough wall surface. It's not really porous. To prevent the microporosity, of course, on the left in picture 1, we can see it's the riser. The riser is the main solution for microporosity. The gating system is another one who has an influence. Why? The gating system will decide where the hotspots will be, besides of the section differences. Very close to a gate, there will be a high temperature, and it's very important to improve the gating system so that the riser can feed it when it's necessary. Pouring temperature, of course, it's not only a matter of porosity, but it's also a matter of energy and cost of the casting. Go about 50 to 70 degrees above liquidus temperature is much enough for having good castings. If you go higher, you will lose energy, you will lose money, and you will increase the tendency to make porosity. Inoculation is very important because the inoculation will decide about the nodule count, and the nodule count is very important for having a good feeding all over the casting, because nodule count is directly related with the fluidability and the possibility of the riser to feed all the areas. And of course, the casting design, you have to discuss with the customer about that there are no abrupt section changes, and that the wall thickness differences from one to another is a smooth one and not a brusque one. Mold hardness, you must make sure that it's strong enough, and that means mainly for green sand you must be assured that the sand is ramped properly. But also in chemical bounded sand, there can be areas who are a little bit difficult to reach, and there is the sand then less good than on other areas, and this can cause problems. Proper sand quality and grain size of the sand decides about the strength of the sand without any problem. Facing the coating, the coating must be, let's say, the thickness of one must be adapted to the thickness of the casting, and it must be applied properly. Again, pouring temperature and the pouring velocity. Pouring velocity is because when you have too high metal speed, it can remove some sand and you can have a problem. Again, well-designed gating and runner system. If we see here the defective casting, it can be inside, under the riser, it can be in a hot spot. Wherever we see here a micro in the middle picture, you see the micro porosity with smooth walls. It's a shrinkage and it can be open and so on. When does it appear? We can see it next slide. Smooth wall is when the carbon equivalent is high. I have the experience that if you have in sections, casting sections above, let's say 25-30 millimeters, and you have a carbon equivalent of 4.5, you will get shrinkage with smooth walls inside the cast. And improper feeding and rising, of course, is here also, but due to the high carbon equivalent, the feeding is disturbed and will have problems to reach all areas. The temperature again is very important, and the section thickness, of course, creating isolated mass or not. Low feeding efficiency, every riser and must be calculated concerning the modulus for making sure that he can feed until the casting is really solidified. But the number of risers is also to be calculated, because every riser has a feeding distance, and a feeding distance is depending on the section of the size of the section of the casting, but also of the liquid quality of the casting. The nodule count mainly is very important there. If that's not okay, whatever riser can be okay, but the feeding efficiency will not be okay. And if proper feeding neck design, of course, we can buy risers now with a conical bottom for the feeder neck, with all types of connections. Make sure that it's okay. And a supplier should really prevent the proper data for that feeder neck design, so that you will have no problems. You have solidification, the delayed solidification. Sometimes we need chills, because a chill is a tool that will increase the feeding length of a riser. A chill never compensates a shrinkage or a porosity. It increases the feeding length of the riser, and therefore, especially in thicker castings, let's say from 30-50 millimeters wall thickness on, it can be very interesting to use chills for decreasing the number of risers you will have to put. Here you see typically how the smooth wall surface is of a microporosity on the left side, and on the right side I have put some pictures, and you see with 4.1 it's more a rough one, 4.3 theoretically it's no porosity, 4.6, you see it's a very smooth wall surface. And if you see microporosity with smooth wall, always first look at your carbon equivalent. Something is wrong over there. Microporosity, it's very, how much they say, very typical for ductile iron castings. And it has in heavy sections, in thermal center, and the last solidification area. That's very, very important. It's always in the last solidification area happening of microporosity. And it's very difficult to compensate that because it's in the area where it appears. There was at the end, there was some shrinkage and the riser could not reach it anymore because there was no feeding possibility anymore, and it will be very small defects coming very close to another, and it can be found by ultrasonic very, very easily. So it's the most difficult defect or porosity that appears with ductile iron. It's the definition is it's a micro is a fine shrinkage cavity network. It's a network. It's not one defect. It's more defects formed during the last stage of solidification due to insufficient feeding and localized contraction. How can you see this if you have, let's say, thermal analysis curve? When you have melted your iron, you put the thermal analysis curve. If you see that curve first drops down the temperature, then goes up a little bit and then drops down. When at the end it drops down too slowly, then that means that at the end, when the last metal is solidifying, there is no carbon anymore coming out of the liquid metal, and no carbon coming out anymore to form nodules. Will be no compensation of this type of shrinkage and will lead to microporosity. So it's one of the defect appearance pictures over there. It looks a little bit like a sponge. This seems to be very, very big, but it's mostly not that big, but it's there, and it's very, very dangerous for the application, especially if you have a pressure tight casting that is pressurized during the use, then it will be very, very dangerous for that. Where will it be? The hot spots, the thin to thick junctions, near a riser neck. Anyhow, it's at the last freezing zone, and it can be in a heavy boss section, but please, it's in the last freezing zone where it happens. It will come out after machining, you can see it, but ultrasonically and RT X-ray will show it. And many times you can also see it under the microscope when you can take out a sample of that, and you can see it over there. Sometimes people think it's about carbon, but it's microporosity. The big impact for your customer is leakage. It's reduced strength, of course, and the machining, when he machines and it touch an area where there's microporosity, the surface condition will not meet the requirements anymore, and then it will be not okay. Of course, an NDT can already scrap the casting before it's used, but it's a very, very dangerous and the most difficult porosity in ductile iron. You can see here some of them that I had from real pictures, and you can see a number of, it's a knit, it's all small, very small porosity, very close to each other. It's mostly far from the riser due to inadequate inoculation. Why? Because I said that if your inoculation is inadequate, your nodule count is mostly too low, and a low nodule count will decrease the feeding length of a riser, and you will get these problems at the end of the feeding length or between two risers. So when no feeding length of both risers touch each other, then it will be there in the center of the two risers. So again, some overview then we see where is it possible. The feeding system, of course, if the riser is not okay, it's already sure, and it's when there is no liquid metal anymore at the moment of solidifying, shrinking. There in that area you can have it. It's sometimes under a riser because the riser neck solidified and the last solidification shrinkage under the riser is not compensated anymore, and then it's under the riser. And that you see in the riser design. If the riser is not feeding until the last moment, he will not be able to compensate these micro porosity. The hotspot, although with the hotspot, it's the last solidifying metal. Let's say there you have first micro shrinkage, and if the hotspot is really not compensated by the riser, then it becomes a macro porosity. So in a hotspot, micro is the start of a micro porosity later. The carbon equivalent, of course, low carbon equivalent increase the shrinkage tendency and reduce the feeding ability of molten metal. For sure, this is, never forget that the nodule count is very, very important. Inoculation practice, we see it over there. If the nodule count is not okay, the tendency will increase a lot. The pouring temperature, as for every porosity, is an important factor, and the hardness of the mold in ductile iron is also important because due to the expansion of the metal in the solidification phase, then the mold can open, and this is an extra volume that cannot be compensated by the risers. And the sections, of course, if the section is too sharp variation from one thin section to a thick section, you can have these problems. It's there again, the key fact is it's formed at the last solidifying metal area, and the feeding was insufficient. So it's in between risers. It's under a riser when the riser neck is solidifying too early, and it can be in hot spot sections, but then it's not, let's say, that big, because in a hot section it starts with micro going over to micro. What's the problem? Leakage, of course, poor strength, machining rejection, and problems with the NDT testing. So sunk in, you can have sunk in, and many times foundries and even customers don't see it when it's small, but when it's big, you really will see it happen. You can see it in the center picture. It's happening when the outside of the section is solidified, and when that's solidified, there is a layer of solidified metal. When it's the metal in between, the liquid metal decreases temperature, solidifies more, it decreases volume, and normally when the surface stays flat, there is a vacuum coming, and vacuum is that strong that it will suck mostly the upper section that is solidified down, and you will see a smooth, small or bigger sunk-in defect. It's when, how must I say, when the remaining section is still sufficient for the customer, it's no problem, but sometimes the remaining section is not sufficient anymore. And sometimes it's like that there is a machining stock, and due to the sunk in, the casting cannot be machined all over because there is too much machining stock in the center, and then the customer will also not accept it. It's a localized shrinkage. It has, you need here that the outside, the metal in contact with the mold must solidify quickly, so that there is a small thin layer of solidified metal who will later make happen that you have this sound. It's about improper feeding, it's about hot spots, and it's again the late solidification, but not that late as the micro shrinkage. It's in between the first solidification and the last solidification. Here are some castings, and there you see really very, very well the problem of this sunk in. And on the right side, you can also see there, it's a kind of a bearing cap in the center of the feet. You lack material, and many times when the customer starts machining, he cannot get a complete machined surface there anymore, and then he will not accept the casting. It has to do with low carbon equivalent. Why has it to do with low carbon equivalent? Because to get a solidified layer at the outside in contact with the mold, it needs a CE who is lower than 4.3, because then we first get a layer building and later the nodules comes out. Where you get it in tin to thick junction sections, in bosses, mainly in bosses, in heavy ribs, in a flange, but it's mainly when there's a thicker area around a riser, but not that much. There I saw it very few times, and then near a hotspot. It's an indication, if you see it, that localized shrinkage is not being feeded by the riser at the moment of solidifying. It's an improper feeding, of course. It's always about feeding. Every porosity is about feeding. A high temperature can also be a reason, because then total shrinkage can be much more than expected. A low mold hardness, again, due to the expansion during solidification, it's possible that we have an extra volume. A hotspot is a very dangerous area for any type of porosity. An incorrect riser design, of course, when the riser is very quickly solidifying the riser neck, then the risk is very, very high that you get that sunk in. And the casting geometry is also important, because if the feeding length of the riser is not sufficient, you can get a sunk in over there. That was about porosity. Now we have air and gas inclusions. Can be inside the section or at the surface. Air inclusions are mostly due to incorrect venting. That's especially when they appear on top of the casting. Gas inclusions are due to the mold or the car, because some of the sand hardening systems or whatever will burn at around 500-600 degrees C temperature, and at that moment there will be gas. If the casting is not solidified at that moment, the gas can enter the metal. Gas and air will always float up to the top of the casting, but if the metal temperature is low or the casting has a complex shape, it can be located all over inside the section. Most of the time they appear only when machining is performed, and then it's not making our customer happy. So you can see here, and the first is air, a lot of air bubbles. The other one is a concentrated air, but mostly gas is also involved in that. The third one below, that had a very, very thin covering solidified section, but when you touch it with a hammer you can see it. And the third one is definitely lack of venting, so that the air is staying there. Always you will have smooth wall on the defect, because it's gas and air, and gas and air doesn't make a rough wall of the defect itself. Where can it be? It can be near the ingates, mostly at the top sections. It can be where there's the thick to thin transitions, and it can be at the hot spots. But let's say in 60 to 70%, it will always be on the top of the casting. A surface, on the left side there is surface porosity. We have said now it should be in the section. The second one is an internal that's coming out when it's machined. The third one is the same. It's coming out when it's machined. And you can have a cluster of gas. When you have that, then it's mostly about a car or a mold who makes a lot of gas in a concentrated area, and there it comes out, and the rest of the casting is fairly good, but somewhere it's due to burning of the mold or mainly the car. It's round and elongated, smooth internal. It's mostly found on a machine surface, as well on the top as inside when there is a car involved. Can occur as isolated pores or a clustered porosity, and it's usually dark in appearance. It's for shrinkage of porosity, really shrinkage porosity, it's not dark, but this with gas and air, it's mostly a dark one. The problems you can have is, of course, leakage, reduced mechanical strength, machining, injection, and definitely your customer will not be happy. So How does it come? It's turbulent pouring of gas. An excessive pouring height can increase the problem. Interrupted on non-steady pouring stream, that's one of the most frequent reason of this. An improper gating design, and with the gating design we also mean venting, because gating we mean the complete system, and the venting is really very important. And a high pouring temperature, that means that the gas or the air can move all over, and will the high pouring temperature can penetrate the coating from a car or the mold, and when it's penetrated and the hot metal comes in contact with the car, you will have gas from the car. So pouring temperature is very important here. Metallurgical causes, of course, high moisture. I don't have to tell you guys in India that during the monsoon season, it's a very frequent defect that every one of you, let's say, happens and appears it will be. Excess of dissolved gases, H2 and N2. The H2 is caused from the humidity. And the next one is a poor melt treatment, but the poor melt treatment is mainly the slack removal. If the slack is not removed very well, slack can be the reason that some more gas or whatever is initiated and stays in the casting. Improper inoculation practice is a little bit less, but can do. And overheating of the melt is, of course, mainly for gas, the reason. Mold and car courses, high moisture in the mold of the cars, think at your monsoon season. Low mold permeability for green sand, because chemical bounded sand has no permeability, mold permeability, so it's mainly for green sand. Insufficient venting is very important, the venting, that it's on the highest point, but also at the end where the metal stream is flowing when the casting is filled, there should be venting. Higher binder content in the sand and car means that if the coating is penetrated and the liquid metal touch it, if there is a lot of binder in it, you will have a lot of gas. If there is less binder, you will have less gas. And for some improper car baking, you can have that the gas comes still there when it's not baked properly. So inclusions, we have put it others because inclusions are here physical things like sand and slag and all the non-metallic materials. Slag, oxides, dross, sand, and everything else that can be entrapped and remain in the casting after solidification. Here, sometimes filter particles are also one of these inclusions. On the right side, we can see the slag can come from the ladle or the furnace. That means it's deslacked very badly. It can be sent from the pouring system due to the high pouring speed and due to the high metal speed inside the pouring system. It can be slag or dross formed during the filling of the casting. We have seen it. Dross is nearly always present in ductile iron, because dross is the combination of magnesium, silicon, and oxide, and it will always be there. Sometimes you can have undissolved late inoculation, and on the other side, what I mentioned already, filter particles. So where does it go? Let's say on the top of the casting. Then it has been floating up very properly, nearly engaged. That means it just entered the casting and could not move anymore. It can be in heavy sections where there is a big amount of metal last solidifying. The last filling zones, that means when at the end you pour in some slag, it will be in the last filling zone of the casting. And many times it's around car prints and cars who have a different section thickness, a very thick section to a thin section, then it can be that it breaks there or the coating is not properly and the liquid metal will break out car pieces and it will be sent to using the casting itself. You can see some of them here On the left side, that's really slack. That's coming from the ladle. On the center, that's slack and even some gas. Wolf, that was a very poor, badly poured casting. And on the right side, you can see it was slack and it went up to a boss who was on top of the casting, and it could not come out of the casting anymore, and it was stuck there. Sand from the pouring system, there is something very, very well seen. On the left side, you can see that an inclusion of bigger sand, there is always a straight line. And when you see a straight line, you can be sure that it's sand, because the sand was bended, broken out, and that breaks always at a straight line. In the center, you can see it the same. When you see some straight lines, it's a big sand who comes out. On the right side, that's, let's say, the speed of the metal was so high that sand grains were continuously breaking out, and they will somewhere go in the casting. In this case, it was a car where it's stacked there, and it gives you that type of view. So dross, we have discussed it already a few times. If you see a casting that had rusted a little bit, and you see these gray on the picture on the left top, and you see these gray areas, that's due to the dross. Why? Dross does not rust, and the metal rust. So if you see that, there is a lot of dross inside of that. At the right side top, you can see it appeared after the machining, and the left side bottom, that's when you see it under the microscope. Dross is always a long extended indication of magnesium silicon oxide inclusions. The rest of the casting, the nodules are perfect, but you see the dross there in between. Right bottom side, that was a casting with a lot of dross, and that's broken to show it, and you see it again that it's the dross who was going to the top of the casting. Yeah, undissolved late inoculation. Sometimes you see it on the left side. You can see it under the microscope. It was the SeO2 who was not solidified. In the middle, you see a casting who was machined, and you find out that some shiny inclusions were there. That's also inoculation. On the right side, that's very few, but it's also there. You see all these white spots all over. That's inoculation who is not dissolved properly. And this is filter particles. You can have on the left side nearly a complete filter who came one reason or another inside the casting. That seldom happens. In the middle, you can see a small part of a filter who broke off and went with the metal inside the casting. And your customer will definitely not be happy with that, because his machining tools will be broken on this particle. It's so hard that it will be breaking. And on the right side, you see somewhat bigger than the middle one, smaller than the other one. But you can be sure that filters who are not properly added or properly, let's say, produced, you can get a problem with them as an inclusion. So the root cause of inclusions, we see the metal related ones are poor slack removal. If you have a lot of dirty return scrap that you use for your melting, the risk is very high that you will get it. Oxide and dross formation during melting, that's one thing, but if you don't remove them from the ladle before you pour, you will get a problem. An improper magnesium treatment leads to oxide films. That means if your magnesium is very high compared to the residual sulfur content that you have, dross is very, very, very high, and to a lesser extent reoxidation of the melt. Because with the magnesium present, the reoxidation will be very few. It's mainly the magnesium and poor slack removal from the ladles. The gating system causes turbulent flow will cause dross, because one of the elements of dross is the oxygen, magnesium, silicon, oxygen, and the turbulent flow provides oxygen, and therefore you make dross. Improper runner design, that's the same. When the metal speed in the ingates, mainly in ingates, is very, very high, you will get again this turbulent entrance of the metal in the casting, and that will be this forming dross. The lack of a slack trap. One thing is very important, and I see it all over the world. Every runner should have a slack trap at the end and under the sprue. If you don't have that, you are asking for problems, because your first metal is dirty, it is in contact with the cold mold, and it will be cold and dirty, and if this metal goes in the casting, you have inclusions for sure. So make sure that you have a slack trap under the sprue and at the end of the runner. No ceramic filter. A filter can, let's say, hold everything in front of the filter, not after the filter. Everything that happens after the filter, it will not hold. And the second thing is a filter, to my experience, does not hold dross, because dross is such a fine with, let's say, composition with a high fluidability, and it goes through the filter. And then an improper ingate and position of cast that can cause the turbulent filling. Mold and correlated sand erosion. That's not only the strength of the sand, but also the speed of the metal who is flowing over it. A low metal strength, of course, the lower the metal strength, it will be, the quicker the sand will go. Core breakage, especially cores who have different sections, and with an abrupt going over from a thinner to a thicker section, there you have the possibility. Loose or weak sands, and the loose sand, I am sure that quite some molds are closed without looking if the sand was removed completely. And many foundries, they have not a sufficient system for removing the last loose sand out of the bottom mold, of the drag mold, before putting the cope mold on top of it. A high moisture content is always negative, because moisture is heating up and it's increasing its volume, and it will destroy the sand or the cores, whatever, the surface mainly, and then sand can break out. The process-related causes, excessive pouring velocity. The metal should never enter the casting with 1 meter per second. Never. And the lower, the better. Even the biggest castings are poured with metal entering speed of less than 1 meter per second. Long holding times before pouring. Of course, the longer you are waiting there, the magnesium is still reacting, and magnesium reacts with oxygen from all over, and eventually with slag, and gives then the inclusion. Improper ladle cleaning. If there is some slag against the ladle wall and you pour in, you tap in new metal, the slag will come loose, and it will be entering the metal and eventually also your casting. And a high temperature, of course, because the higher the temperature, the quicker the sand will be attacked, the more the dross will be formed. High temperature is always a negative thing. So cracks, you have the hot crack and the cold crack. What's the difference? The hot crack is initiated at the time or just after the time of solidifying. So it means it happens when the metal is solidifying but has not yet strength enough to, say, hold the stress of shrinking, and then it can happen. The cold cracks are initiating at low temperature. It's mostly lower than 500 degrees C, and it's mainly with heat treatment that it will happen, or sometimes during, let's say, the cooling down in the mold, and we have a very thick section compared with a thin section, there it can also happen. Hot cracks, cold cracks, stress cracks, that means that's mostly a cold crack also, and a heat treatment crack is also a cold crack. It can be linear on a surface. When you see it over there in a flange, it's hot crack over there. Somewhere it happens there when there is a defect inside the casting. During the solidification, the defect acts as a crack initiator, and it can crack over there. At sharp corners, of course, you can have it there, and it can be lack of shrinkage possibility, or at the moment it becomes just solidified. The same with the third casting near a riser junction. There it's mostly a hot crack that you have, and an internal crack, as you see at the right side after machining, that has always to do with the defect, mostly porosity, who is inside the casting, and then during the solidification it acts crack initiator, and it's due to the stress. You can see on the left side that's a hot crack X-ray picture. The second is a hot crack seen on the casting itself. The third one also, and fourth one also, and that's due to defects. The fourth one, the right one, is due to defects, so that it cracks to the outside. So cold cracks are, you can see them much better. They are mostly closed, much more closed than hot cracks, and it has to do with lack of shrinkage. It has to do with heat treatment. It has to do with stress during the cooling and in the mold, so that it hinders the shrinking and it cracks. You can see it there in the bottom. You had the porosity over there, and from there on the crack starts, and it's a stress crack. Yeah, again, where it happens, it's sharp corners, or of course the most important area where it can happen, where the section thickness change, and when it's very abrupt change, it's one of the things that it's really happening there. Car prints are also many times to a crack. Near a riser, then you have a hot crack. Rib junctions is a matter of, and bosses is a matter of difference in section sizes. And in heavy section, you can have the hot spots during the cooling. Now, I must say that cracks are in ductile iron much lesser frequent than in steel or gray iron. Where are the root causes? Design-related, sharp corners, insufficient fillet radius, of course, sudden section changes, unbalanced design, and stained contraction. These are all potential causes. Metallurgically, a high carbon equivalent variation, let's say the higher the carbon equivalent, you can have more possibilities for defects, other defects, and defects can, during the further shrinking and cooling down, the start of cracks. An improper nodularity, that's known. The better your nodularity, the less problems with cracks. Carbide formation can also act as a starting. Low magnesium level, that means the same. If you have a low magnesium level, you have an improper nodularity. And poor inoculation, then when the nodule count is very low, then the crack grows very quickly, because a crack grows from one nodule to the other. If there are only few nodules, the crack length will be immediately higher, and the higher the crack length, the quicker it goes further. Process causes uneven cooling, of course. You need the difference in temperature. Excessive mold restrain that you have mainly with chemical bonded sand, that sometimes it's impossible for the metal to shrink, and then there will be a crack. Low pouring temperature, that I should call it, it's a crack, but it's can be, let's say, a cold crack, in the sense that two metal strings who touch each other and there is some oxides in between, they will not connect it properly. So it looks like a crack, but it's a different cause due to the low temperature. Improper shake-out timing, of course, if you shake out and you hit them by whatever, it can be that it will crack. And a high pouring rate is mostly then that with a high pouring rate, you make dross, you make other inclusions, and inclusions are the initiators of cracks later. Mold and car causes, a hard mold of a car. Poor collapsibility, of course, then the casting cannot shrink. Improper car support, that can also be a high car print stress. If that's really a high stress over there, it's a possibility. And low sand permeability, that means everything always in, and you get more inclusions, and if you get more inclusions, the crack can start much easier. test methods. You have destructive testing. I should say it's not.
Okay, the first question is by Mr. Suresh Babu. Hi, sir. We are producing ductile iron bracket samples for a German customer. Grade is 450 by 18. Tensile strength, yield point, and elongation are safety characteristics in the drawing. Your suggestion on the chemical composition to be followed. I have checked with him. He said the weight of the casting is 38 kg and average section thickness is 20 mm.
I always start with a chemical composition as it's mentioned in the Sorel publication. They have a publication there, and depending on different wall thickness, I'm sure Kastwel must have it. There are suggestions you have there, and I start always from that. Sometimes I change a little bit. My starting point is always the suggestions as are in that Sorel, let's say, sheet.
So, Mr. Suresh Babu, what we will do, I will share with you the composition available with us, and you can unmute yourself. And if you have taken the trial and if you have faced any problem, you can describe that. So, Mr. Hendrieckx can give a proper answer on that.
Please, if you have a problem, let me know, and then we can find out what small modifications we can do to have a better result.
Yes, sir. Am I audible? Sir, this is for a German customer. They want these three characteristics as the minimum requirement in the drawing. Tensile strength, yield point, and elongation. All three has to be achieved. So we are trying with high silicon and low manganese and low copper. We are pouring some test bars, but we are achieving either of the two of the three parameters. We are not able to achieve all the three parameters. If you achieve tensile and yield, elongation is missing. If you achieve tensile and elongation, yield is not able to achieve. So that is we are taking some trials. Silicon above 2.8% silicon we are putting. Manganese up to 0.3% max. Copper we have added up to 0.15%. So we are able to achieve only two of the parameters out of three. So that's why I requested your inputs.
But sir, I propose, please give tests you have done to Kastwel, that they send them to me, and I will comment on each of them and propose you a better solution then.
Sure, sir. Okay. Right, sir.
Please do it like that. I will answer then very quickly.
Sure, sir. Thank you.
Okay, Mr. Suresh Babu. Yeah. Thank you, sir. So you can note down the address. It is a sales at kastwel.com, on which you can send your composition which you have tried and what kind of results you have achieved. So based on that, Mr. Hendrieckx will give you the detailed answer.
Sure, sir. Yeah. Thank you.
Thank you, sir. Now the next question is from Mr. Jait Langardar. Sir, please share the remedies to avoid carbides in a ductile iron casting for thin section parts.
One of the things over there, who is mainly the root cause of carbides in a thin section, is a too high magnesium residual content. That's let's say, in my experience, it's in 60-70% of the cases, it's a too high magnesium. Thin sections doesn't need a very high magnesium residual magnesium content, and what you have to do there is what I call the magnesium active. We have seen it in previous sessions. Magnesium active is the magnesium from your spectrometer minus 0.75 the residual sulfur, and that should be definitely 0.03 or a little bit less. If it's higher, you will have carbides. And the other thing then, let's say this is the main reason. What can be another reason is, let's say, a pouring temperature or too long running of the metal from the ingates to fill the casting. That can also be a reason.
Now, sir, the next question is from Mr. Jignesh. What are the causes of liquid shrinkage in the casting? Cause of liquid shrinkage.
Oh, that's okay. You have first that when the casting is filled, when you stop pouring, from that moment on, every shrinking of the casting of the metal, and that's 1.5% per 100 degrees C, the metal decrease. If you stop pouring, that metal, that decrease must also be compensated by the riser. And every metal has that. A liquid on a higher temperature than the liquid is temperature, if it decreases, it's, let's say, shrinking. For iron and steel even, it's 1.5% per 100 degrees C. This shrinking, you have to compensate by the riser. And then you have, from the moment you meet the TL temperature, the liquidus temperature, up to the solidus temperature, there it depends on the carbon equivalent. Metal with a carbon equivalent higher than 4.3 has in principle not a solidification shrinkage. But that's theory. There is always some small. But if it's lower, if your carbon equivalent is 4.1, 4.2, to say something, then you also get the solidification shrinkage. Then you have your liquid shrinkage from the pouring temperature or the temperature the moment the casting is filled, up to the liquidus temperature, 1.5% per 100 degrees C. And then during the solidification, extra shrinkage or expansion due to the carbon equivalent.
By Mr. Tarun Kumar Maduru, he is facing a problem of macro porosity with smooth surface defects coming in majority in one production unit, which is a green sand unit, and it is coming in all the part numbers. This defect is coming. So what could be the causes and what should be checked? He has shared the picture of the castings also. I'll share on the screen.
The ramming of green sand is very, very, very important. Why? At a certain moment, if the ductile iron is solidifying, at a certain moment it expands. When the carbon is coming out to form nodules, it expands. And that means that expansion, depending on the section thickness of the casting, is mostly higher than the strength of the green sand. If that strength of the green sand is low, it will be pushed out somewhat, and you lose extra volume that cannot be compensated later anymore. And if you say it's at one of its foundries and other maybe not, first look at how good is the green sand rammed. What's the hardness of the green sand? And secondly, don't put a higher carbon equivalent than necessary, because the higher the carbon equivalent you have, the more the expansion will be. And then even sometimes chemical bonded sand cannot withstand it. So it's a matter of compare the hardness of the sand, the green sand mainly, with the carbon equivalent you're using for these parts.
There is one more question. What should be the last box minimum pouring temperature for SGR and machine molding? This has been asked by Mr. Chandrasekhar Veerabhadran.
I have the experience that I should never pour at a temperature higher than 70 degrees above the liquidus temperature. Now, depending on, let's say, the section thickness of the casting, the sand, if it's green sand with a lot of humidity, and the metal has to flow very long inside the casting, I should say take 70, 80 maximum. And if it's not that much, you can go down to 50 because you know if it's 50 degrees above liquidus temperature when the casting is filled, it's 0.75% of liquid shrinkage you get. And many times I always see that, let's say, 80% of the foundries pour too high temperature because they are afraid for cold run, but they don't realize that they create a lot of shrinkage by taking that high temperature.
Mr. Veerabhadran has to study about what is his pouring temperature, tapping temperature, and what is his pouring temperature, and where the losses are there, and accordingly he can correct the temperature.
The point is, if he pours more molds with one ladle, there is a big difference between the first mold and the last mold, of course.
Then Mr. Karimullah Babu has asked how to avoid a thick to thin section micro shrinkage.
By a good radius, and for, let's say, that's a design mistake, we as foundries, We try to do a lot of things, but it's never a complete solution that we can find it. The only thing is a good radius over there, and making sure that in that area the sand you are putting there is not heating up too much so that it makes gas. That's the only two things I can give you, but it's a very difficult problem. And if the design is bad, it will always have a high amount of rejection.
Till then, we will take a next question by Mr. Nagbhushan Pappu. Is there any relation between hardness of S-cast surface and UTS?
For ductile iron, no. No strict relation, not like in steel. In steel, there is nearly a formula to do that. For ductile iron, there is no good relation.
Okay.
There is a very wide range, so the relation is nearly, I should say, there is no relation.
Now we have Mr. Mohammad Ilyas. I would like to present the chemistry. He said that sir, tensile strength and elongation failure reason on the same chemical composition and no visual defect in the test bar. What is your recommendation? He has given the chemistry. It is a 500 by 7 grade.
I am looking at your carbon equivalent. It's very higher.
But sir, his question is with the same chemistry, he is getting a good casting, and with the same chemistry, he is having a failure in tensile strength and elongation with the same chemistry. Yeah.
Let's say if you have once a good casting and once a bad casting, you do something different. And if it's not the chemistry, but there will be a difference in the chemistry, and look especially at magnesium to sulfur ratio, that's already one. If there is a difference, the nodule count and the nodularity are very important.
Now, Mr. Vijay Purohit has asked, normally to improve the yield, sleeve is placed directly on the casting, and in such case, we found a flakes below the sleeve. So how to avoid it?
If he finds there flake graphite, that means that most probably has he a breaker core under it, or is how is the riser? I can give some possibilities. I know if there is flake graphite under the riser, that means and the other area of the casting is still okay. That can only be one thing, that there is a reaction of the riser sleeve or the breaker core of the riser sleeve with the metal, and there is something in it that causes it. I don't know exactly what. I know that several of the breaker cores have a reaction on the metal and react with the magnesium, so that it ends up with flakes, and it's because it's too long liquid over there. But it has to do with the riser sleeves. Some suppliers have not a good riser sleeve for that. In Europe we have had that problem also, and then I don't know anymore just like that what point it was, but there was a certain product in the riser sleeve that was good for the riser sleeve for making it happening, but that reacted with the metal and made flakes. There must be a reason why a nodule becomes a flake there, and that can only be by an interaction with something, and that's with the riser sleeve or the breaker core.
Then Mr. Karimullah Babu is again asking how a molding sand hardness can influence rough surface, microporosity, or sunk in.
Let's say microporosity and sunk in, it's about the same root causes. The only difference is when you have a sunk in, part of your surface of the metal must solidify immediately. When it solidifies immediately, then it can be pushed in later. That means it has to do about the carbon equivalent and the type of sand. If you have green sand with a high moisture content, there will be much quicker surface layer who is solidifying. If you have the metal with a low carbon equivalent, it will also solidify quicker. So these two reasons make that it becomes a sunk in instead of, let's say, a very big micro shrinkage.
He's asking how mold hardness can influence.
The mold hardness can only, let's say, influence, to my opinion, the size of the micro shrinkage. Why? When the sand is not strong enough, then it's pushed open. I must say it now from my head, but let's say I think that green sand has a compression strength of about 1.5, 1.7 megapascal. Now, expansion from a casting can be easily 3 megapascal, 4 megapascal. So when you have that, then the sand is pushed open. When the sand is pushed open, that means the volume of your casting increase. And that volume, increase of volume, comes on top of the normal shrinkage of your metal. And that causes mostly a micro shrinkage. And we are talking only about 1% or 2% extra in that area.
We will take a last question by Mr. Nagabhushan Pappu again. Then which ferrosilicon magnesium is good for heavy castings, rare earth base or lanthanum base?
In previous sessions, we have also covered that subject. I know that rare earths or cerium or lanthanum, one of the two, that are very good elements in thin to medium sized castings. I have from castings from 100 millimeter section on, I always use ferrosilicon magnesium without rare earths, without lanthanum, without cerium. That's one of the points. The second thing, it seems that lanthanum in thin castings has a lower tendency to form chunky graphite than cerium. But I have not seen a very, very sharp difference between them. I have used it very, very few because lanthanum is costing more and I did not find the benefit of it.
Yeah, thank you everyone for joining us today. If you still have any queries, you can contact myself, Amish Panchal, or Mr. Hardik Panchal. Our mobile numbers are shared over here.